Try this one on. Let's see, we got a mass equals 2 kilogram compressing a spring with a force constant 800 newtons per meter, a distance of 0.2 meters from its natural length. When the block is released, it travels down. Down, that means I've got a height. If I've got a height, that means I have gravitational potential energy already. I don't even know what we're doing yet. I just know that. It travels down a rough incline that height equals 4 meters high. The block's final speed after descending the incline is v equals 2 meters per second. I know what kind of energy that is. How much work was done by friction? All right, when I read those words, work was done by friction, or work was done by whatever, that just means how much energy was dissipated. And in this case, was dissipated by friction. That's how you should be reading this. By friction. So how much energy, I think I forgot the important part, was dissipated by friction on the block as it slid down the incline. So to figure that out, we need to figure out our energy before, our energy after, and then whatever's missing is going to be the energy that was dissipated by friction. Let's check it out. In the beginning, what kind of energies do we have? We have gravitational potential energy for sure because we have a height. We have a spring potential energy because we have a spring and it's compressed. So let's go ahead and figure out our before energy. Call this before. We've got mgh times 1/2 kx squared. M is 2 kilograms. G is 10, so 20 times the height, 4. 20 times 4 is 80. These two are added. Plus half of K, spring constant, is 800, so half of 800 is 400 times 0.2 squared. 0.2 squared is going to be 0.04 times 400 is going to be 16. So the total energy before is going to be 96 joules of energy. What about after? After it slides down. We know the speed right here is 2 meters per second. We know the mass. All we have down here is kinetic energy. Kinetic energy equals 1/2 mv squared. Half of the mass. Mass is 2. Half of that is 1 times 2 squared, which is our velocity. So kinetic energy equals 4 joules. We have much less kinetic energy after than we had total energy before. How much less? That is the amount that work done by friction was. So friction removed 92 joules of energy from this system. So the work done by friction, or a non-conservative force in this case, is negative 92 joules. Negative because we are losing that energy to the environment. For the next part, a spring hangs vertically. A student connects 3 kilogram block to the spring and then gently lowers the block until it reaches equilibrium. I need to draw that. We've got a spring and we got a block. Lowers it until it gets to equilibrium. Okay, so it started up high and then it went down to equilibrium. We'll call this EQ for equilibrium. Once at equilibrium, the block remains at rest and stretches the spring 0.2 meters. So this distance here from here to here is 0.2 meters. Don't worry about that. We're going to let UG represent gravitational potential energy of the block spring earth system, and US represents spring potential energy as mechanical energy in this block spring earth system conserved during this process of lowering the block from the unstretched spring to equilibrium. Show yes or no, including calculations, and then use words to explain. All right, so what do we know? We know that whenever an object is at equilibrium, whether it's a spring or not, then all of the forces are canceling out. So at equilibrium, we have gravity going down. What kind of force do we have going up? Spring force. Those two equal each other. Spring force, if you remember, the equation for that is K times X. Your spring constant times your displacement. We have our displacement. Good. And the equation down here is just mg, as usual. Now let's look at the energies. when it's connected up here and then it gets lowered, what's happening to the energy? Well, we're adding in this spring potential energy because now that spring potential energy is being stretched beyond its natural length. It's being stretched 0.2 meters. So writing in the types of energies that we have, if we set this as height equals 0, then this height equals 0.2 meters. At 0.2 meters, we have height, so we have gravitational potential energy. And when we're at h equals 0, we have spring potential energy. Remember, the equation for spring potential energy is 1/2 kx squared. So how much energy are we getting by allowing the spring to expand? It's going to be whatever this is, 1/2 kx squared. We don't know what k is. Ah, nuts. First, let's get k. We're going to do that by looking at our vertical forces, because we know our spring force equals our gravitational force, so that means kx equals mg. This is an important reminder that any force equals any force, whatever the occasion is. F equals F. Spring force equals, in this case, your weight force. Spring force could equal your frictional force if it was balanced and horizontally. Spring force could be your centripetal force if it was spring was pulling the object in as it went in a circle. You can set any of the forces equal to each other for this trick. All of this will also equal mass times acceleration. For us, though, it's going to be useful to get k. So we have m, which is 3, so 30 divided by 0.2. So k equals 150 newtons per meter. Newtons per meter. So what about our spring potential energy? Spring potential energy is going to be 1/2 kx squared. Half of k is going to be 75 times 0.2 squared, which is 0.04. So my spring potential energy is 3 joules that I'm gaining, that the spring is gaining as it goes down. Meanwhile, while it was up at the maximum height, we had gravitational potential energy, which is mgh. mgh, 3 times 10 times 0.2 is going to be 6 joules of energy. So at the very top, in the beginning, we had 6 joules of energy. If we brought the spring up, we would have 6 joules of energy. If we let it go to equilibrium, we would have 3 joules of energy. So what's going on here? In this case, the hand is doing negative work. So as the student is bringing the spring down, they're doing negative work. Energy is being lost because we have more energy before than after. So that means, because work is a change in energy, which is final energy minus initial energy, if the initial energy is more, then you're going to end up with negative work. Negative work. So the hand is doing negative work to remove energy from the system. And in this case, we have force going up, the spring force going up, and the displacement is down. So again, they're opposite directions, which means negative work. So we're losing some of our energy as that work is being done.